Good afternoon, Rad Lab students. I wanted to make this video that'll pertain to our lab on measuring the radiation from a piece of Trinitite. And from that, you should be able to estimate the atomic bomb yield from the first nuclear device ever tested by humanity. So on July 16th, 1945, the Trinity device detonated in the New Mexico desert. And it was a mighty blast, and it fascinated and horrified all of the investigators and researchers and engineers who created the first atom bomb. It impressed J. Robert Oppenheimer so much that he uttered the famous lines from the Bhagavad Gita, which is part of the Hindu scriptures. And he said when he saw the detonation, he said, "I am become death, the destroyer of worlds." And on the aftermath of that, when that all cooled down, they went to the blast site and they found some of this wan, sickly green glass in the desert. That the atomic bomb blast had such heat intensity that it vitrified or rendered in the glass the silica that was there. And so what we want to do is counting the radiation from this and using the Bragg and Atkatz paper that you'll see for experiment 7 in your manual, you will be able to estimate the atomic bomb yield using the activity that you count from this piece of Trinitite that was actually from that blast site. Now this is kind of an example of what sometimes physicists call a Fermi calculation. It is a back of the envelope calculation that actually gives you some interesting and real estimations of some sort of a physical phenomenon. And, but it has to be such a calculation that it's measurable. It's not just a complete guess, but there needs to be a way to actually measure what it is. And so the atomic bomb blast is estimated to be about 20 kilotons. And you can look that up to verify that. But what I want to do then is count the radioactivity of this. Now you'll observe over here, I have taken a spectrum of cesium and cobalt. So this is the 662 keV cesium 137 peak. And these two peaks represent the 1173 keV and 1330 keV peak from cobalt 60. And so what you will find is we will count the cobalt 60 peak from the Trinitite. So I will remove this, and I will put in the Trinitite, and this will fit in the following way. It'll fit in very, very close to the detector. In fact, I'm even going to try this. It probably won't fit in that first stage. But I'm putting it on stage 2. And now what you will notice is that approximately the solid angle encompassed by the Trinitite is 2 pi. Now if you did your experiment yourself on stage 2 and you know what solid angle is encompassed by your sample, you can probably use what you did earlier in the lab. But the Bragg and Atkatz paper suggests to use a solid angle of 2 pi. Now what I want to do is call that spectrum back up. And I'm going to clear it. And now I'm going to collect again. And so the voltage needs to be on. So I'm going to turn the voltage on. And you'll notice some radioactivity starting over here. Now this is going to be a very long count. The cesium-137 has a 30-year half-life. It's been well over 2 half-lives since the atomic bomb test in 1945. So the cesium peak is going to be very, very weak, and we need to count for a long time. In fact, I'm going to count this for a solid hour. And you can see here a few dots that represent the cesium peak starting to rise. So I'm going to go over here and zoom in. Okay.